Today in this video we are going to see about reflection two-ray model. Introduction. Free space propagation model is an accurate in many of the cases when used alone. The ground reflection model or two-ray model is designed for both line of sight and reflected rays. This model is accurate for predicting the large-scale signal strength over distance of several kilometers. Only assumed the earth is to be flat. This image shows the two-ray model. T is the transmitter and R is the receiver. The distance between the transmitter and receiver is D, and the height of the transmitter from ground is HT and receiver is HR. ELOS is defined as energy in line of sight. Electric field in free space propagation is E of d, t equal to E naught d naught by d cos of 2 pi fc of t minus d by c, where E naught is the free space electric field and d naught is the reference distance. Considering that Ht is the transmitting antenna height and Hr is the receiving antenna height. Electric field in line of sight path is E naught d naught by d1 d dash cos of omega c of t minus d dash by c, where d dash is the separation distance in the ground, c is the speed of light in vacuum and omega c is the carried frequency. Electric field in reflected path is given by the reflection coefficient gamma E naught d naught by d double dash cos of omega c of t minus d double dash by c, where d double dash is the separation distance in reflected path and gamma is the reflection coefficient. Activity. Total electric field is given by E total is equal to E line of sight plus E reflected path. In this equation, the minus 1 is the coefficient, reflection coefficient. By using method of images, we find the path difference del, which is given by del equal to d double dash minus d, where TR separation is very large compared to HT plus HR. The equation can be simplified by using Taylor series approximation, and del is given by 2HT HR by D. Once the path difference is known, the phase difference between the two electric field components and time delay between the arrival of the two components can be computed. Theta equal to del omega c by c and time delay tau is equal to del divided by 2 pi fc. Line of sight versus reflected path. When d becomes larger and larger, the difference between the d dash and d double dash becomes very small. In this case, the amplitude levels of both line of sight and reflected rays are virtually identical. Therefore, E naught d naught by d is approximately equal to E naught d naught by d dash, which is also approximately equal to E naught d naught by d double dash. Received power and path loss. The received power at the distance d from the transmitter for the two-ray model is given by PR equal to PT GT GR HT square HR square by d power 4. The path loss is given in this equation. Assessment questions. First one, what does path loss exponent indicates? Option 1, rate at which path loss decreases with the distance. Rate at which path loss increases with the distance. Option C, rate at which path loss decreases with power density. Option D, rate at which path loss increases with power density. The second question is, difference between the direct path and the diffracted path is called. Option A, average loss. Option B, radio path loss. option C excess path loss, and option D wavelength. Thank you.